Hello, Charles here. In this video, we'll be going through Chapter 6, which introduces some extensions to the bivariate model, which by now you are well familiar with. So in this chapter, we'll be looking at some different specifications like regression through the origin, as well as log-log, what we call log-log or log-linear models, etc. And some models that are not necessarily linear in variables. Then we'll also look at scaling of regression coefficients. And then also lastly, there's a word about the choice of functional form towards the end. Okay, so the first alternative specification we'll look at is regression through the origin. And this is a specification that is similar to what you've seen before, except that it omits the beta 1 term. So as you can see in the equation up on the slide here, there's no beta 1 hat in this model. Instead, this model has only a slope coefficient, beta 2 hat. In other words, we're setting beta 1 hat to 0. And this type of model will be useful in many instances where it's reasonable to assume a beta 1 hat value of 0. So in the example given below the equation, we have interest earned in a savings account. And in the specification given there, while it's somewhat simplistic, it just sort of illustrates the point. If we take interest earned as a function of the balance in a savings account, when there is 0 in the savings account, we cannot expect there to be any interest earned, right? In other words, if we have x equals 0, then in this case, beta 1 hat must be 0. And you can think of other examples where this type of model might be appropriate as well. In the lecture notes, for instance, I mentioned the production function, which is something that you might be familiar with from your second year macro course, which specifies output as a function of production factors. And of course, when production factors are 0, you can't expect there to be any output. So again, we would expect a beta 1 hat value of 0 if we were to empirically estimate a Cobb-Douglas production function. Now, when using this model, there are a few things to be aware of. Firstly, the R-squared value, the coefficient of determination, can behave a little bit strangely when specifying a regression through the origin. In fact, it can take on negative values, and it loses its usual interpretation. In general, the specification is not one that is advised unless there is a strong theoretical reason for applying it. Also, there are ways of overcoming the issue with the R-squared, but we won't deal with that at this stage. All right, the next topic in Chapter 6 deals with scaling and units of measurements. And this section just gives you some guidance on how to rescale estimated coefficients if you want to change the scale of the variable used in the estimation. And you can think of reasons when this may be useful. So, for example, if a researcher estimates a regression that uses variables like GDP and investment, say, and these variables are measured in billions of rands, and you happen to have data that is measured only in trillions of rands, and you've already estimated your coefficients, and yet you want to compare your results, say, to the research out there. How can you do that? One way to do that is to rescale the coefficients, and you can do that using the formulas introduced on this slide. And in fact, well, here they are. So let's say you want to rescale your y variable to y star using some weighting factor, and you want to rescale your x variable to x star using some weighting factor. Okay, so the important thing to know here is W1 and W2, right? So you have GDP as a function of investment. Let's say that you've estimated this model measuring both variables in trillions, and you want to compare your estimates to the estimates of a different regression model where the data used were measured in billions. Variables used in your model will have a different scale, right? Have a different unit of measurements. Trillions of rands versus billions of rands. So you want to come up with some kind of weight that will allow you to directly compare your estimates to the estimates of the other model, which use a different unit of measurement. Those weights on this slide are called W1 and W2, right? So these, that's where the W comes from. So think of these as weights that you use to rescale your estimates, okay? So that they are directly comparable to estimates measured in different units. All right. So the rescaled values, we denote them with a star. We call it Y star and X star. Okay. But what we are interested in is rescaling the parameter estimates, right? That's what we're really interested in doing. And the way to do that, well, on this slide, we just give you the formulas, and you can look at the lecture notes if you want to know how we derive these formulas, as well as the textbook. If you're really interested, I won't expect you to derive them, but it's useful to take a look and see if you can derive them yourself. But on this slide, we simply present the formulas, okay? So if you want to rescale your slope parameter from beta to hat, this would be your estimate. Then you need to apply the formula given over here, right? So you want to end up with beta 2 hat star, which is now measured in billions rather than trillions. To do that, you have to use the formula beta W1 over W2 times beta 2 hat, right? And if you want to rescale the beta 1 hat variable, you have to apply the formula in this column, right? So beta 1 hat star equals W1, whatever your scaling factor is, multiplied by W1 hat. So in the example we're looking at, where we have GDP as a function of investment, we estimated our model with the measurement unit rands trillions, right? So both GDP and investment were measured in trillions, okay? Now, if we want to convert that to make it comparable to estimates that were determined with units of measurement in billions, so some other researcher ran the same regression, maybe for a different time period or whatever the case may be, it's the same model, but both GDP and investment were measured in billions rather than trillions. So you want to convert your beta 1 to make your beta 1 hat and beta 2 hat comparable to the research that you want to compare to. You want to convert yours from your measurement scale from trillions to billions, right? In other words, you want to determine a Y star and an X star, and by implication, a W1 and a W2, such that you can apply these formulas over here, right? Okay, so in this case, again, the simplest way to do this, to think about what the value of W1 and W2 should be, is to ask how many billions fit into 1 trillion, okay? So how many units of the scale or the measure to which I wish to convert to fits into my current scale or my current measurement unit. Okay, so how many billions fit into 1 trillion? Well, 1,000, right? So W1 in this case equals 1,000, and it turns out that W2 in this case also equals 1,000. Why? Because both X and Y are measured in trillions, right? And we want to convert both of these to billions. So it just so happens that both of these values equal 1,000. Right. So that's how to find W1 and W2, and that's the most important part of doing these conversions, right? Doing these scale changes. Okay, so notice at the bottom here that the coefficient of determination is scale invariant. There's no W1 or W2 in the right-hand side of the conversion equation there, formula over there. All right, but in all the other cases, whether it's the parameter estimates, the variances, and of course the scaled standard error would simply be the square root of the variances of both the constant and slope parameter estimates, or whether it's the estimated value of regression, or as it's called here, the variance of the error term. All of these formulas contain either just W1 or W1 and W2, or in the case of the, All right. Okay, so the next slide just gives you some rules of thumb, some implications of these formulas, and when you read these, I guess you can call them lemmas or just results really from these formulas, try and match them to the actual formula on the previous slide, right? So the first point is that the scaling factors are equivalent, then the slope coefficient and its standard error remain unchanged, and the intercept and its standard error are scaled by W1. Right, so that should be sort of obvious, and it is in fact the case in the example here where both W1 and W2 are 1,000, right? Because the ratio W1 to W2 must be 1 if W1 equals W2, right? So in that case, the slope parameter won't change. Beta 2 hat star will equal beta 2 hat. And similarly, the standard error for beta 2 hat star will equal the standard error for beta 2 hat. However, beta 1 hat star will equal W1 times beta 1 hat, okay? And that's what this first point on this slide is getting at. The next point is if the X scale is unchanged and the Y scale is changed, then all parameters and standard errors are scaled by W1. Again, that follows directly from the formula. So remember, the X variable relates to W2, the Y variable relates to W1. So if W2 is unchanged, in other words, you can think of W2 being equal to 1, then beta 2 hat star now equals W1 times beta 2 hat, right? Because W2, in this instance, given that the X variable isn't changed, the way to think of that is that W2 equals 1. And because of that, all variables are simply scaled by W1, all scaled variables. And by variables here, I mean the estimates, the model estimates, and the standard errors or variances, and the variance of regression. They're all scaled by W1, okay? All right, then the third point says that if the Y scale is unchanged and the X scale is changed, the slope coefficient and its standard error are scaled by 1 over W2, but the intercept coefficient and its standard error are unchanged. Again, looking at the formulas, this is just sort of obvious, because in this case now, W1 equals 1, okay? So the constant parameter doesn't change, so beta 1 hat star equals beta 1 hat. However, the slope parameter now changes by 1 over W2. Right. Let's look at an actual example. On this slide, we have a regression model, a demand function. We have cans of Coke regressed on its price. Now here it tells us that cans are measured in millions, and millions of cans, that's the Y variable over here. So that's labeled Y. And then the X variable, which is price, is measured in cents per can. Right? So the way to interpret this regression output here is that if price increases by 1 cent, then demand goes down by 2.2 million cans, right? Very price elastic demand equation here. So now we are asked to determine how these regression results change, that is the estimates and the standard errors, if consumption is measured in thousands rather than millions, and price is measured in rands as opposed to cents, right? So again, we just apply this, the same reasoning we did in the earlier example. We ask ourselves how much units of the measure we are changing to fits into our current measure, okay? So remember, so taking Y now, firstly, in other words, trying to determine W1, it's measured in millions. So the question is, how many thousands fit into 1 million? And the answer to that is 1,000, right? We have 1,000 thousands in a million. Next, we move on to the x variable. We can ask how many cents are there, or how many rands are there in 1 cent? And here the answer is 0.01, right? It's 1 over 100, which is the values given over here. Okay, so W1 is 1,000, W2 0.01. Most important is to try and get an understanding of how we got to those values for W1 and W2. Right? We asked the question: how many units of the measuring scale we're changing to fits into the existing measuring scale? Okay, and whatever that may be. This slide just sort of shows us how we arrive at the values for for W2 and W1, right? So for the x variable, it says if x is 300 cents, then x star is 3 rands. Okay, so x is the original measurement scale, it's in cents, and then you can ask yourself, well, if that is the value for x, if we want to reinterpret x in rands, in other words, we want x star, then how would that number change? 300, what happens to 300? What becomes of 300? Well, the 300 was measured in cents, so if we want to measure that in rands, we simply divide by 100. Okay, or another way to put it is to multiply by 0.01. In the case of y, in this example, if y is measured in millions, you can put any number here, even 1. In this case, on this slide, it says 7.5, but it doesn't matter what the number is. If y is measured in millions and y star is measured in thousands, what do you have to do to the number associated with that measure so that the value remains unchanged, right? So if you have a value of 7.5 million, right, that's the number together with the measure, it gives you the value, 7.5 million. You want to change the measure from millions to thousands. What do you have to do to that number so that the value remains the same? In this case, you have to multiply by 1,000, right? Because 7,500 thousands is the same as 7.5 million. So that's another way of arriving at W1 and W2. Okay. Then it's just a matter of plugging numbers into the formulas to arrive at the rescaled values for beta 1 hat, beta 2 hat, their variances, the standard errors, and the variance of the regression, right? Again, the R squared is scaling invariant, remains unchanged. This slide just gives you the answers. I won't go through them. This is literally just plugging in W1 and W2 into the formulas. And the most important thing is that you just know how to arrive at those values for W1 and W2. Right? Once you have those, and you want to rescale your estimates and your standard errors, it's just a matter of plugging values into formulas.